Deformation and kinetic simulations. To form various metallic shapes, deformation of metals is necessary. The deformed, or mechanically worked metals are much superior to cast metals from which they are produced. Understanding what happens during deformation and controlling the shaping of metallic materials is an interesting and important issue for both researchers and industries. We show you in the following an example of deformation simulation. Such simulations can help us, not only to understand the phenomena behind thermomechanical processes, but also can quantify material changes during processes.
During deformation, the dislocation density in the system increases, resulting in diffusion enhancement. Furthermore, the dislocations may orient themselves to subgrains and during the subsequent healing process transform into new grains and recrystallization. Here, we focus on simulation of dislocation formation and their influence on the precipitation kinetics. Simulation of the influence of deformation on creating new grains, and its effect on subgrain structure of the materials, will be demonstrated in other videos.
As an example, we take the model system of Fe, with 0.1 weight% carbon, and 0.1 weight% niobium. This will be deformed during cooling in austenite range with a strain rate of 1 per second, and the strain of single deformation operation of 0.1. The deformation will be applied 3 times in temperature range from 1000 to 1100 degrees Celsius.
Create new workspace by clicking on the New Workspace button at the top of the recently used workspaces list. Next, read the data from the thermodynamic and diffusion databases. In Menu Global, click on Databases. In the new window, select MCFETDB database by clicking on Open button. Then, select the database and click on Open button. Select carbon and niobium from the elements list. On the phases list, select BCCA2, FCCA1, liquid and cementite. Click on Read button to read the thermodynamic data. Next, select Diffusion Data on the left and click on Read button again. Select MCFEDDB database on the list and click on Open button. Close this window by clicking on Close button. A quick review of the phase summary window reveals that an additional phase FCCA1-01 was created by MatCalc, next to the 4 ones that were selected from the database. In Phase Details window, the composition of this phase is given, which corresponds to the niobium carbide phase. In Menu Global, click on Composition. In the new window, select Weight Fraction on the bottom, the in % box should be checked. Next, enter 0.1 for carbon and niobium contents. Close this window by clicking on OK button. In Menu Calc, click on Set Start Values to obtain initial phase fraction values. Next, click on the equilibrium icon and click on Go to find the thermodynamic equilibrium for the system at 1000 degrees Celsius. The result in phase summary window shows that 2 phases are in equilibrium at this temperature, FCCA1 and FCCA1-01. The values of phase compositions displayed in Phase Details window reveal that the former phase represents austenite, while the latter represents niobium carbide. Click on Stepped Calculation icon to open the Step Equilibrium window. The default settings define the calculation between 400 and 1600 degrees Celsius with a step of 25 degrees Celsius. Click on Go button. Next, click on Create New Window icon, switch to the User Defined tab. Select the third item on the list, O1 All Phase Fractions, over T Celsius_log Y, and click on OK button. The plot window appears with the equilibrium phase fractions displayed on logarithmic scale over the defined temperature range. It can be seen that region where austenite occurs as a single matrix phase lies in temperature range around 900 to 1400 degrees Celsius. Below 1300 degrees Celsius, niobium carbide phase is also stable. Let us start with the definition of the precipitation domain. In Menu Global, click on Precipitation Domains. In the appearing window, click on New button and give a name to the new domain, which I will simply call Matrix, confirmed with a click on OK button. The phase FCCA1 will be selected for the thermodynamic model of this domain. Next, switch to MS Evolution tab and select Substructure tab. In Substructure Evolution Model field, select 1 param, Shersneff, Long, Kozeshnik ABC model. Finally, click on OK button to close Precipitation Domains window. Now, let us define the precipitate phase. In Menu Global, click on Phase Status. In the new window, select FCCA1-01 phase from the list on the left, and click on Create button on the bottom side. A window appears with a drop-down list. Select Precipitate there, and click on OK. New phase FCCA1-01P0 appears on the list. Select FCC-A1-01P0 and click on Nucleation tab. In the Nucleation Sites area, uncheck the box with bulk description and check the one with dislocations description. Click on OK to close the phase status window. The last thing for the kinetic simulation is the definition of the simulated heat treatment. In Menu Global, click on Thermomech Treatments. Click on New button and name the treatment, which I will just name TMT. Confirm the name with a click on OK button. Then, click on New Segment button and double-click on the segment data that appeared in the data field. In the new window containing the data for the very first segment, type 1400 in the Start Temperature field. Next, set the end temperature to 1100 and the cooling rate to 0.1 in the respective fields. In the Precipitation Domain drop-down list, select Matrix. Click on the plus button followed by a click on Yes button to create a new segment. In the next segment, set accumulated strain displacement, in ramp control area. Leave the heat cooling rate at 0 and accumulated strain to 0.1. Next, click on MS Evolution tab, and set 1 in EPS dot field, which represents strain rate. Create the third segment, in which end temperature and heat cooling rate is defined in ramp control, while the end temperature is set to 1050 and the heating rate to 0.1 again. In the fourth segment, accumulated strain displacement is set again in ramp control, with 0 for heat cooling rate and 0.1 for accumulated strain. Again, set 1 for EPS dot. In the fifth segment, the system will be cooled further to 1000 degrees Celsius with a cooling rate of 0.1 maintained. While the sixth segment describes once more the deformation with accumulated strain of 0.1 and strain rate of 1 per second. Finally, in the last segment, the material will be cooled to 900 degrees Celsius with a cooling rate of 0.1. Click on OK button to close the segment editor. The whole treatment can be reviewed on the diagram in Preview area, and the list, in Data area. Click on OK to finish the heat treatment definition. To avoid confusion, remove the plot with equilibrium phase fractions, before the kinetic simulation will be performed. Next, click on Microstructure Simulation icon. In the new window, select from TM Treatment option button, and select TMT, from the drop-down list nearby. Next, click on Go and confirm this decision with a click on Yes button. In this simple system, The calculation proceeds quite smoothly and is completed after few seconds. Let us visualize the results on the plots. Click on Create New Window icon, switch to User Define tab. Select the fourth item on the list. 03 Kinetics 4 frames TFNR, Linux. And click on OK button. The plots containing the time evolution of system, temperature, precipitate phase fractions, number densities, and mean radius appear in the new window. Let us add a new one, to get the complete picture for the result analysis. Right-click in the plot window area and click on New Plot in the appearing menu. In Variables window find, the dd.tot matrix variable, representing the dislocation density, which is located in Prec domain struct sc variable group, in the dd.tot section. Drag and drop this variable on the newly created plot. For a better overview, change the y-axis scale to logarithmic. With a click on the plot axis and choosing log from the drop-down list in the type line of the Window Options window. Displaying y-axis in the logarithmic scale allows to recognize the range of the dislocation density variation, which extends over 3 orders of magnitude.
Starting from the last plot, we can see the dislocation density curve showing 3 peaks. These correspond to the dislocation formation during the deformation segments present in the simulation. The dislocation density decreases after each deformation segment, due to the healing process. Looking at the phase fraction plot, the curve there does not seem to be influenced by the deformation, reaching the value over 0.001 and rising mainly after the introduced deformation. The effect of deformation is seen on the plots of number density and mean radius. Number density curve rises to the value over 1e19 precipitates per cubic meter, indicating 2 vertical sections at 3,500 and 4,000 seconds corresponding to the deformation at 1,050 and 1,000 degrees Celsius. This is due to the fact that dislocations are the nucleation side of this precipitate, so that an increase of their number results in the increase of the nucleation rate. Moreover, there is a limit on the minimum y-axis scaling of this plot set to the value 1e10 in the plot initializing script. Once this is removed, the vertical section of the first deformation, around the time of 3,000 seconds, is also observed. Mean radius plot indicates the influence of the deformation on the precipitation growth. First, at each deformation segment, the mean radius decreases, due to the formation of the new portion of small-size nuclei. Shortly after, these precipitates grow very fast, due to the increased diffusivity in the system thanks to the increased dislocation density in the system. This characteristics of number density and mean radius is typical for strain-induced precipitation. You can learn more about how to work with MatCalc by viewing other example videos. Thanks for watching.